So today we are going to discuss on the combination and sequential circuits, part of your digital electronics, which is needed for DFT and a little bit of basics. And we are not going to touch something that we don't need as part of your DFT career. Okay, so let's not concentrate on something that we don't need. We'll concentrate on only what we need as part of your DFT. Okay, right. So the combinational and sequential circuits are something that you create or you write a code for using these logical gates. So yesterday we have seen the logical gates. Okay, so these combinational and sequential circuits are the building blocks of any SOC design. Okay, so how do we design? I think part of your academics who are coming from EC EEE might have known this. Okay, or from masters who have done on VLSA, you might have an idea of this. But simple logics. Okay, let's see basic combination circuits. We start with a basic understanding of inputs and outputs that you can get from the combination circuit. Okay, so this is these combination circuits are designed using the logical gates with a functionality expectation of bringing up a functionality, either a addition or subtraction, so any arithmetic operation. Okay, so whatever in ALU, arithmetic logical unit, can perform and what we want it to be performing. Okay, in terms of the end product, a calculator. Okay, how much operations a calculator has to perform. Okay, it's a mobile. So mobile processor, the arithmetic logic unit of a mobile processor, how many computations it can perform, that many logic we can build, we can write it using these combinational circuits. So let's start with basic combination circuits of half adder. Okay, so half adder is a combinational circuit which performs binary addition with the two inputs and produces a sum and carry. So let's look at the truth table of half adder. So does this resemble any of the logical gate? Team? This behavior, do you see any logical behavior from the logical gates? XOR gate. Right. So 0, 0 and 1, 1 will always, if either the inputs are active high or active low, then your output is low. Okay, but given the half adder, we get a proper carry when you get a active high inputs. Okay, for that we have A and B to be AND gate, so that when both inputs are high, okay, you get a carry. Okay, and you take some from the XOR gate output. So it is simple circuit, just have to realize. Okay, and the equation of sum and carry, like A XOR B with A slash B plus A B slash, you get A XOR B, and carry is just A B, which is an AND gate, the same representation of your logical gates here. Let's see the complete adder, a full adder. Okay, so a full adder It's a combination circuit which performs binary addition of three inputs and produces sum and carry. This particular representation, you see, it's a three input full adder. Okay, A, B, and C input, which is a carry input. So whenever this is a proper addition that you see, whenever there is a 1 and 1, your sum will go 0 and will get a carry on. So similarly, we have all the truth table, and based on the truth table, you have to draw the logical diagram. Okay, and based on the truth table and logical diagram, you can have an expression, or from expression you can have both of these outcomes. But otherwise, first truth table comes in the first place. Okay, any circuit, first you need to draw the truth table, then you start with logical expression and logical diagram. Okay, so you see that there are two XOR gates and two AND gates and one OR gate. So totally we have 5 gates. Through these 5 gates, we are able to create a full adder which exactly represents the truth table. Okay. So sum is A XOR B XOR C, and carry is a multiplication of this AC plus BC plus AB. Okay. Again, the half subtractor, the difference and the borrow compared to the half adder. Subtract is something similar, but as we subtract it, we get the difference. And if you want to subtract from a higher value, then we have to borrow it. Okay. So only 0 and 1 will get a scenario where we borrow. Okay. The rest of the situations, either it is 0, okay, or a difference of 1. So what we have is an XOR for AB, and the carry, we have an AND gate with one of the input. We have NOT gate. The dot resembles the NOT gate. If you see the full subtractor, you can see we can also do K-maps for this. Okay. So A, B, and B in, the borrow in, the D output, and the borrow output. It's a full subtractor. Okay. So 0 and 0 will never have an issue. Okay. And from 0 and 1, we have D output of 1 with a, which is borrowed. So we have to mention the borrowed value as well. So similarly, if we go through all the truth table, we will be able to see that A XOR B, B XOR B in is the same equation, but borrow out will have AB, B bin, and A B bin. So it's similar representation of a full adder, but the operation is addition and subtraction is the only difference that we see here. So coming to DFT, you don't need to understand K-maps, as I said before. Okay. So what you need is you should be able to write the basic RTL code for a half adder or a full adder or a 4-bit counter. And must and should you need to understand the Verilog code, writing Verilog code for all the logical gates, demux, D flip flop, and delatch. These are the must. Okay. So coming now to the multiplexer. Multiplexer is like multiple input and single output. Okay. So generally we start with two by one mux, where we have two input, one output with a select line of either of the inputs. So we'll have only one select line for two inputs. So it's a very simple and most helpful and useful uh, I mean, very useful multiplexer where we will be using extensively in our designs. Okay, you will be working as a DFT engineer. You will be working through your entire life in a DFT on multiplexers more. Multiplexer plays a key role in the DFT. Okay, so multiplexer, advantage of multiplexer. Let me just explain a scenario in real time how it is helpful. Okay, so there is a clock 1, clock 2. Okay, so this is my D input, Q output. Okay, reset, set, clock. Okay, this is my clock input. Now I have two clocks. I need to categorize, I prioritize which clock to drive. So I need only one clock to drive at a time. Okay, this is some 500 megahertz. This is some 1000 megahertz. Okay, so I get the selective line where I can select which one to allow. So my select line, okay, is either 0 or 1. So when I select 0, clock 1 will pass through and reach to this particular clock. It will drive. Okay, in the real time usage. Okay, similarly, if you take reset, reset 1, reset 2, data 1, data 2. Okay, these are the major situations that we use these muxes. Okay, majority of the time you will be using 2 by 1 mux. Okay, we haven't come across any situation where we have used more than 2 by 1 mux. Okay, so most of the time it will be 2 by 1 mux. We make designs simple, will not make it complicated. Okay, so we are not designing RTL design where we can have more than one more than two inputs. Okay, we will make it simple here. So 2 to the power of n will be inputs and 1 will be the output, where when you are making it 2 to the power of, it will always multiply by 2. So it will always be 2, 4, 16 likewise. So let's see the truth table on block diagram and internal logical gate. Okay, so the block diagram of 2 by 1 multiplexer is something that I had drawn before. This is just a block representation, but actually the mux is something like this, right? Okay. Now, the operation I have already explained you. So look at the logical diagram. We have two AND gates and one OR gate, and there is an NOT gate for a selective line. Okay, so this is very simple logic we can realize based on the behavior of the multiplexer. So the multiplexer logical circuit, the combination circuit, is designed using three gates, or you can say four gates including NOT gate. Okay, but generally NOT gate is not considered much as a gate count, so we call it as a in semiconductor we consider more of it as a buffer, okay, with the opposite value driving towards wherever you are trying to deliver it. Okay, so AND gate, OR gate, and a NOT gate. So you can do multiple, let's say, equations, and you can make it 2 input to 4 input. You can bypass certain inputs and bring out the expected output. Okay, generally we wouldn't be needing this, so we'll not be discussing much on this. Okay, so for a 4 by 1 multiplexer we will have two select lines. Okay, so select line, now we have a chance to select using 0 0 0 1 1 0 1 1. You can assign each one of it to the inputs, and you can take the expected output. So based on the truth table you can have the expression, and based on the expression you can have the logical diagram. As you see, there are 4 AND gates and 1 OR gate and 2 NOT gates for each select line. Now let's see on the demultiplexer. Here, even the demultiplexer, we will not come across demultiplexer in DFT, but let's just look at it just for a revision. It's the exact opposite of multiplexer. So one input, multiple outputs. So for a 1:2 demultiplexer, it's the same as 1:, like uh, you can have n is equal to n is to 2 to the power of n, where your multiplication will be always depend on the n value. So if you have one input, we'll have two outputs. So this demux and mux are mostly used in A to D and D to A conversions. Okay, so I mean at a larger scale where you need multiple inputs, let's say 6-bit, 8-bit, 10-bit, 12-bit, 16-bit. Okay, data, if you need to, normally we'll go with multiplication of 8. So 8-bit or 16-bit or 32-bit or 64-bit. Then you will have a larger multiplexer or demultiplexer, part of your functional logic. Okay, so we do not actually bother about DFT uh, DFT doesn't bother about the functional logic. So in your SOC design, okay, which is this RTL code has been written for entire processor, entire ALU, everything, all the modules. Okay, this is a functional logic. Okay, so this is functional logic written by RTL engineer. Okay, so we only try to understand this, but we don't modify RTL logic, or we don't uh, care why this RTL logic is written for. What is the functionality behind it? We don't care actually. What we care is the RTL logic is behaving as it should be, and whether we can test it or not. That is what we will check. Okay. So for that reason, we have segregated RTL logic as functional logic, and the DFT logic that you insert as part of your DFT insertion as a DFT inserted logic. So what we care about is only the DFT inserted logic, which will be simple logic gates and multiplexer, 2x1 multiplexer, and a flip flops. So that's what I was saying. Logical gates, mux, D flip flop, and D latch. Okay, only these are the things that matters for a DFT engineer. Okay, so we should be very clear on what we are inserting and how do we insert it. That we'll learn part of the course. Okay, but as a prerequisite, let's understand each and every combination circuit. Okay, and after that we concentrate on particularly what we need. So this is 2x1 demultiplexer, 1 by 2 demultiplexer, and this is the where we have to use an encoder, n input lines with n output lines. It's a combination circuit then that can assign a unique binary code for the active input line. Okay, so encoders, decoders are extensively used part of your SOC design. Okay, let's see a 4x2 encoder. Okay, so a 4x2 encoder will have 4 inputs and 2 outputs. In 4 input lines, one input line is set to true at a time to get the respective binary code in the output side. Okay, so let's say you want to decode it. Okay, so you have to mention, you have to program only one input line. Okay, so if you program one input line at a time, you can get the respective output. So you have two OR gates back to back connected. I won't say back to back, it is a cascading connection. So Y1, Y2, Y3 will be active at a time to produce A0 and A1. Okay, you program the other input, the encoder. Okay, let's see how it is in a priority encoder. A proper priority encoder that we use in real time in RTL design. So highest priority input will be from the ratio of D3, D2, D1, D0. D0 is the lowest priority input. Okay. So if you see that the Y0 output is entirely depending on the D1 and D3. It's an OR gate. D1 plus D3 will give you Y0. But as a priority encoder, what we can do is D0 has the lowest priority and D3 has the highest priority. So when more than one input is high at the same time, output will be corresponding to the highest priority input. So when you say Y1, it is a combination of D3 plus D2. Okay. And Y0 is a combination of D3 plus D2 and D1. So a decoder is also a combinational circuit that converts a n-bit binary input code into 2 to the power of n bit output. So we'll see a 2 by 4 decoder, the truth table behavior. Okay. So decoder is much more easier actually in terms of realization from block diagram to truth table and truth table to the logical diagram. So each D0 is equal to D0 is a lowest, right? So uh, here you start with the lowest one in the decoder and D0 becomes the lowest priority and D3 becomes the highest priority. But you get the output, exact output, the opposite output similar to the behavior of an AND gate. Sorry, similar to the behavior of an OR gate. Okay, for a D0. So again D2 A not B and D3 A B not and D3 D2 A B not and D3 A B. So with respect to the same, you can create the circuitry by adding NOT gates and using an AND gate. So this is a comparator. So you can compare with either A is equal to B, A greater than B, A less than B. You can compare A and B values giving to this particular comparator. So when, as per the truth table, when both inputs are low, the output is high. Okay, which makes that A is equal to uh, B. So 0, 0 and 1, 1 will make it the value equal. And 1, 0 will make A greater than B and 0, 1 makes A less than B. As simple as that. So you just create the schematic as for that. Coming to sequential circuits. So compared to combinational logic circuits and sequential circuit is something that it has a memory element. Okay, so there is a memory element. So what do you mean by memory element? In this context, what is the memory element? How many memory elements we have? Anybody? D flip-flop. Sorry, I mean, we're taking a D type. So it's a flip-flop and a latch. We have only two type of memory elements. Okay. So generally, can anyone explain the behavior of this D flip-flop and a latch? Anyone? You can just explain what is D flip-flop and what is a latch, or at least give an answer for the difference of D flip-flop to the latch. Because we spend more time again next to the mux, we spend more time in DFT on these two elements. I would say 80% of our DFT depends on this D flip-flop. And latch plays around 20% out of 100, and out of 100, 80% of DFF. Again, if you take mux, plays around 60% out of 100. Okay, individually. Okay, so apart from mux, we have other elements which covers the 40% for in this category. Those are logic gates, which cause 40%. In these two come under one category, in which 80% is DFF and 20% latch. Okay, so flip-flop is a memory element, okay, which has the data input, output, and it works with a clock. Okay, clock input would be a pulse. Okay, so it would be a proper clock pulse. One clock pulse. Positive half cycle and negative half cycle. Okay, so when you provide clock, that to the active edge of the positive edge of the clock, this particular D flip flop, okay, this is a pause edge D flip flop, which means the data gets toggled. That means you are giving input at this place, which is a 1, let's say 1. 1 will be stored in this flop, okay, as well as come to this position of Q when you give one clock pulse, and that too a positive clock. That means when you're giving a clock, the data toggles at the active edge of the clock pulse. Okay. So on a complete one cycle, the value is stored and it comes to the queue. If there is a connectivity to another flip flop, it reaches to this particular flop input. It not saved in here, it just reaches. Okay. So sequential circuits are something which are meant for representation of combination plus sequential circuit, the memory element. Okay. Now, if I give one value here, and this combination logic circuit is some, let's say there are two inputs. Okay, 1 and 0. This is your AND gate followed by an OR gate. Okay, and you have a memory element at the output of this AND gate, and there is one more input coming here, right? So this is one more 1. Okay, so this AND gate output is 0. 0 is value is stored here, the memory element, and you are providing a clock. So again, 0 and 1 makes one output here, 1 goes as output here, and again this one value can be fed again to this memory element. Okay, and this can go back to here. So you can see that if you, based on the arrows, if this is the way, what you can do is you can change the circuit here. Sorry. Okay, so this particular one input memory input is coming from this memory element. So 0 and whatever the previous value stored here, it is a 1. Okay, then 1 will go 0 and 1, 1. So this kind of circuit is called, it's a feedback loop. Okay, so it's a feedback loop. Your value is coming to this memory element, and memory element output is going back again to this combination circuit as input. Okay, so this will be a loop. Okay, so when you have a memory element in a circuit, that is called sequential circuit. If you don't have any memory elements in the circuit, that is purely combination circuit. So as simple as that. Okay, so combination circuit output depends only on present inputs because it doesn't have any memory elements to store. Sequential circuit depends on both present input and present state. Okay, so present state comes when you have a memory element, right? So the sequential circuit always depends on the memory element value and which state it is. Feedback path is not present for combination circuit. Sequential circuits have feedback paths. Memory elements are not required for combination circuit. Sequential circuits, memory elements are required. Clock signal is not required for combination circuit. Exactly, remember this point. You do not need any any clock signal to drive the combinational circuit. That means there is an AND gate. You just give value, you get the output. You don't need clock pulse to drive this value. Clock pulse to drive this value. Okay. So this is important. Common circuits are easy to design. These are screen circuits are difficult to design. Okay, and many of these things are not exactly. These are academic way. Sequence circuit doesn't necessarily need feedback paths, but feedback paths are most commonly used in sequence circuits. That's what it means. Okay, not necessarily sequence circuit need to be having feedback path. Not necessary. Next, coming to latches. Before going to latch, I wanted to discuss on the flip flop. Okay, particularly D flip-flop. So, are you guys there? I'm not able to get any response from anybody.
Sir.
Okay. Please be active. If somebody is not able to get, if somebody is new to these things, just let me know. Okay. So this is a D flip-flop. The short form we call it as a DFF. Okay. So D flip-flop. D flip-flop has one data input, clock input, reset, and set. There will be one set. Okay. So the data input depends. I mean, the data input, whatever you are giving 1 or 0, has to be captured and stored in this particular flop because it's a memory storage element. Okay. And the stored value can be utilized or move forward if you give one more clock pulse. Okay. 1 plus 2, 1 pulse to store and 1 plus 2 forward. Okay. So if there is one more flop here and it has a clock as well, if it is the same clock, just you need 2 clock pulses for this value to be stored in coming back to here. Okay, let's say 0 and 1 are the two inputs. So 1 will first go here in first clock pulse. Okay, and in the second clock pulse, this one is already here in first clock pulse. This will go into this, it will shift, right shift to the next carrying flip flop, and 0 will come here. Okay, so likewise, we'll be dealing with shift registers going forward. So D flip-flop plays a major role in the entire DFT. Okay, because our entire work is based on this D flip-flops only. So this is very important. Please learn. Okay.
Sir, could you please repeat once more?
Okay. So D is a data input. Okay. Let's say you are giving. I'm adding one more. Okay, I'll stick to the initial flop. Okay, this is a single flop. Okay, you want to load one value. Okay, some binary value. Let's say 1011. Okay, you want to load this value, but this is to load 4 bit of data. You have only one flip flop, right? To load 4 bit of data, you need 4 flops. Remember that each flop can store only 1 bit of data on a at a time. At a time means on that particular cycle. So you need one clock pulse, okay, to store 1 bit of value. So 1011, the first immediate value, okay, 1 will come to this place when you give one clock pulse. If you give one more clock pulse, okay, 1, 2. Again, the next value will come and this value will go move on to the next cascading, okay, series of flop. If there is a connectivity, if not, it will just go to a combination logic gate if there is a combination logic gate and it will be captured in the output. Okay. Next, on a third cycle, you will have this 0 coming in as data. Okay. Now in third cycle, the data stored in this flip-flop is 0. In the fourth cycle, what is the value? What is the value of fourth cycle?
1.
1.
Right. And a fourth cycle, you will have one value. Okay. So 1, 1, 0, 1. You got it? Okay. So this is the behavior of a flop storing a value, and how we store a value by giving in the clock. Okay. Now, another thing I want to explain here itself, there is a reset. Can anybody tell the purpose of reset in any circuit, not just analog, not just digital, analog or anywhere? I need an example also in real time. Can anybody give an example of reset? Any example?
Clearing of data, sir.
Okay, clearing of data. So in terms of this particular digital circuit you are mentioning, right? So when you
Yes,
say reset, okay, if there is an initial data of 1, when you give reset, what happens? What is our active value now here?
0.
0, correct? Okay. So initial value is always 0. Remember that. Okay. In digital circuit, initial value is always 0. Your 1 means you are putting some value. Okay. Even that might be, even 0 might be active value, but you consider 0 to be a reset value in the when you are using reset. So resets are used across analog, digital, anywhere to, if you even in your mobile phones or any electronic and electrical gadgets, okay, circuits that you see, there will always be a reset. Okay, particularly analog and digital circuits, we will have this reset. Analog, the purpose is different. Okay, digital, particularly resets were more helpful in the digital part to reset the RAM. Okay, the cache memory or the processor memory. Okay, whatever, however you want to use, you can use it. So any program you have written so far, like you are programming your IC, a 16-bit IC2 with a 16-bit of code, let's say 1011101111. When you do reset, okay, so far whatever value has been stored in the flops, all will be reset. Okay, and you have written a code that you don't want to be erased, then you will not program reset for that. You don't want it to be reset. Okay, so there are many ways, whether you want to protect the data or you don't want to protect the data. Okay, reset is used only for the flops that you want to reset. Okay, by default you take in the RTL design engineer while writing the code and synthesizing it, he will take a D flip flop with a set and reset, and the reset is active low. Okay, we will learn this going forward. Okay, don't worry, we'll be working more on our flip flop part. Right, so JK, yes sir, we don't need to worry about this. We are not going to work on any other flip flop because D flip flop is the most stable flip flop output that we can get out of all other flip flop types. So flip flop is a 1-bit memory cell. To increase the storage capacity, we have to use group of flip flops known as registers. Okay. So registers are something that you have created using a group of flip-flops. And the n-bit register are having n number of flip-flops and are capable of holding n bit of words. Okay, so these registers are, in general, we call it as a shift registers. Okay, they are connected back to back. So either serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Okay, so the binary data in a register can be moved within a register from one flip-flop to another flip-flop. Okay, in a serial connection, which will allow the register to transfer the data from one flop to another flop. So let's say this is your circuit. Okay, and you have sequence of flip-flops connected back to back. Okay, this is your primary input port and this is your primary output port. You give how many flops you have? 5 flops. So 5 bit of data you have given and you collected 5 bit of data here. Okay, so you can store value, you can store the bit of data here, and you also can also collect it based on the number of clock pulses you can give to drive the value to the next. Okay, so these are called shift registers. These are shifted to the right. Okay, and we have different way of representing these shift registers. Serial in, serial out. This is one that I explained. We'll see the all the types. Serial in, serial out, connected back to back circuit. Okay, where both data loading as well as data retrieval to or from shift registers occurs in serial mode. Okay, that means you given data here and you collect the data at the output, and it will have a single clock, the same clock driving all these flops in a sequence. Okay, next, serial in, parallel out. That means you don't want to wait until the last flip-flop output. Instead, you can collect output of every flip-flop at this stage only. Okay, so you are giving 1010 value. You can collect this 1010 at each flip-flop output. Okay, for that, every time you can clear the flop after collecting the value from each flop output. Okay, this is serial in, parallel. So remember guys, this serial in and serial in, serial out, serial in, parallel out, these are useful in your simulations. Okay, remember this, we will be discussing again back in only simulations. Okay, so there is other thing is parallel in, serial out. Okay, let's see how parallel in, serial out works. So you can take the value from a combination logic circuit from parallel in, that means data is coming from parallelly. That means the input of each flop is coming at a time. Okay, parallel input you are getting, and you are collecting the serial data in a single data bus like this. Okay, so they will be having load mode, shift mode. Okay,
So then why do we use logic gates, sir?
logical gates are representing here the Q0 and Q output. you are collecting them and you are giving it to the second next cascading flip-flop. You can see here. Q0 of this particular flop is collected here and given to his OR gate and again fed to the D1. Okay. So depending on the mode again, you want to shift or load. So loading means loading in the data input. Okay. While loading, you only load value. Shifting is you are completely load mode is off and you are only using this as a shift register now. You are in a shift register mode. So when you are shift register mode, okay, this value will become like shift is 0 and load is 1. Okay. So when you use that value, whatever this value you get, you shift the value output. So this is used in compressor. Actually, the LFSR concept also we use this EDT compression. We'll be discussing it in compression time again. Okay. And we'll also use in simulations also, parallel simulations. So these are, we use it for parallel monitoring instead of serial in serial out. Sometimes if serial in serial out has issue, we try to do parallel monitoring. Then we dump out parallel in and serial out patterns. Okay. So these logic gates are helpful in parallel out, but in real time, in terms of DFT, we do not have any kind of additional logic, okay, to create this functionality. Instead, what we will have is we will directly stitch Q0, okay, to flip-flop 2 and Q1 to flip-flop 3 and Q2 to of this particular flop to flop 4. So we'll have serial. We will not have any of this logic. Okay. Because this is a complex functionality which represents like muxing. Okay. But we will have mux here already. Okay. So I'll explain that in a DFT scan architecture. Okay. This structure is only possible and implemented in RTL designs. Okay. But in DFT, we don't use this architecture because each flop has internally one mux that is called scan mux, which we will discuss in DFT. Okay. So we don't need this architecture. We have the selective paths of shifting and data. Okay. Data loading and shifting, we have two paths. I'll explain, we'll discuss that on a later stage. Okay. This is the general behavior of parallel and serial out. Is this clear? No, not clear. Team?
Clear, sir.
Is everyone clear on this? Should I explain
Yes, sir.
again? Okay. So as you can see, there is a load mode where all the inputs are passed to the corresponding flip-flops when the second, fourth, and sixth and gates are active. So these gates are active when the shift or load bar line set to 0. So this architecture is designed in such a way that it accommodates the functionality of shift and load using fourth and sixth AND gates. Okay. See, 2, 4, 6. These gates are active when the shift or load bar line set to 0. Okay. So here we need to only load values into the resistors, the input values. So we will give values to the B0, B1, B2, B3, which is this 1011 are coming here. Okay. So you see this architecture. Okay. B1 is coming from an AND gate and reaching here. B2, same. B3. Okay. Now shift, once loading is done, now we move to shift mode where the second, fourth and sixth gates are inactive when the load and shift line set to 0. So 2, 4 and 6 goes to inactive and only 1, 3 and 5 are active during shift because 1, 3 and 5 are connected to the outputs of each flip-flop. Okay. Next, parallel in, parallel out is simple. You give data in the D input and directly capture data at the Q output of each individual flop. So in real time, we use serial. I will make it short. SISO. In DFT, I'm telling PIPO in general. These are called, SISO is called serial patterns. Okay. And PIPO is called parallel patterns. When we want to debug certain serial patterns or parallel patterns, we will go with serial in, parallel out, or a parallel in, serial out. Okay. So this is the mechanism supported by the tool. Okay. To produce the required patterns, but there will not be any design logic inserted in the design because, as I said, each flop will have one mux internally, the scan mux. Okay. I will tell you this architecture later. Whatever the DF, the D flip flop that we will be using in a real time will have a scan mux inside. I will discuss that later. Okay. Is this clear? We are moving on from this resistors, shift resistors. Is it okay?
Yes, sir.
Okay, sir.
Next is counter. So counters are also used in our real time and extensively used in our designs. And DFT uses counters in a very rare case, but yes, we'll use it. So, but understanding counter is important. Majority of the times in interviews, they ask about counters. Okay. So a counter is a device which stores the number of times a particular event or process has occurred, often in a relationship to a clock signal. Okay. So counters are basically used to count the number in a sequence Okay, so we use it for digital electronics for counting purpose. Okay, or specific event happening in the circuit. Okay, so we have up counter and down counter. So up counter will increase 1, 2, 3 for every rising edge of the clock. Okay, so not only counting, a counter can follow the certain sequence based on our design. Like if we set up a sequence, okay, it can also do that. Okay, so we generally use counters for clocking circuits in our designs in real time. Counters are used for clock circuits, particularly frequency dividers or a clock dividers. You call frequency dividers or a clock dividers. Okay, so these are the sequential circuits. You will have counters will have sequential circuits. Okay, uh, let's see how this counter works. So let's start with asynchronous counter. Okay, so asynchronous counter. Okay, so the data is not stable. It always depends on the previous flop output. Okay, so there is a constant clock coming into first flip flop, and flip flop output is going as input to this clock input to the next flop. Okay, generally we don't use this at all. We don't use it at all, but we might use it in a case if you want to have a irrelevant or asynchronous clock architecture. Okay, only then we will have this. So if you see, if there is a one value here and the clock is coming, okay, so let's say this is your active clock and one is going as a clock. That means you have again an active clock. Okay, again this is one. So logic one is loaded here. One, this is a one. Okay, so in a initial one clock pulse, okay, here in example we have taken it's a zero value. Okay, because this is a negative clock pulse. Okay, this is a neg edge. Neg edge. Okay, negative edge of the flop. Okay, so this is a negative edge of the clock. Okay, negative edge is here. So the one value is loaded here and is active until the second, complete one clock pulse from here to here. Okay, next, the QB. For QB, it has to wait until two clock cycles. Okay, because the first flop output is going as a clock to the second flip flop. So you need to wait. In the second clock pulse of the second active clock edge, negative clock edge, okay, your value is captured. Okay, so in this stage, the value of 1 is stored for the consecutive two active clock pulses. Okay, because you are getting continuous active only one value throughout. Okay, let's see synchronous counter. In real time, we always use synchronous counters because clocks has to be in a synchronous stage to allow the data to be in synchronous. Okay, in the synchronous counter, the same clock pulse is passed to the clock input of all the flip-flops, and the clock signals produced by all the flip-flops are the same as each other. Okay, let's see. This is one clock architecture. You see J, K, and Q. We have taken JK flip-flop as an example. Okay. Even if you take a D flip-flop also, it will be very clear actually. Okay. So the data will be synchronous across, but this will act as a clock divider circuit for us, synchronous counter. So you can take the output of Q0, okay, as one clock, and this is second clock output, third clock, and fourth clock. Okay, so this is the slowest clock. Okay, so if you take the output of this particular clock, okay, Q3, you will get 100 MHz. Okay, this is a Q0 1000 MHz. Okay, 1000. You will have 1 3 is a 1 nanosecond is a 1000 MHz. Sorry, let me just okay. So this is 1 plus 2.5. This is 2.5 nanoseconds. Next again, this is 6. So this is 1, 2, 3, 4, 5, and 5.5 second. Consider the 5 nanosecond here. 5.5. Again, this is somewhere here in 12 clock pulses. Okay. You are in many 12 nanoseconds. This is far beyond. Take it as a 24 nanoseconds something. Okay, so 2.5 is a 500, and this is We are getting 100 megahertz and even less. This is going beyond, let's say, around 25 megahertz. Okay. So it's a 2-bit synchronous counter in which the two inputs of the first flip-flop FFA are set to 1. So the first flip-flop will work as a toggle flip-flop. The output of the first flip-flop is passed to both the inputs of the next JK flip-flop. I don't know why JK flip-flop is taken into consideration, but we generally use D flip-flops only, even in real time. Okay. In real time, it is all D flip-flops. We never use any other flip-flop other than D flip-flop in entire circuits. There will not be any JKS or any other type of flip-flops. Okay. So let's move on.